Welcome back, Focus learners. Listen, today we are doing something totally different. We are stepping straight into the high-stakes corporate boardroom of Cambridge physics. I want you to imagine right now that you are pitching your exam answers directly to a board of ruthless principal examiners. In this room, you can't just guess. You need to justify every single point with hard data, logical progression, and absolutely bulletproof strategy. In this explainer, we are completely unlocking the examiner's playbook, specifically focusing on mastering the conservation of energy. And look, whether you're tackling the core 0625 syllabus or you're working through 0651, 0652, the 5054 O level, or even setting your sights on the 9702 AS level, the foundational strategies we are covering today are going to completely change how you write. Now, picture two incredibly common types of students sitting in the exam hall right now. First, we have Alex. Faced with a complex, multi-stage energy transfer question, Alex totally panics. Alex overloads the paper with raw physics facts, aggressively dumping every single equation they've ever memorized onto the page, but completely lacking any real analytical structure. It's a mess. Then, on the other side of the hall, we have Sam. Sam is obsessively watching the clock. Sam rushes through the question, completely misses the specific command word requirements, and just slaps down a final number. Both of them are leaving huge, massive chunks of marks right there on the table. Today, we are going to look at their flawed answers, literally highlight the red pen marks they'd get, and completely transform how you approach these critical exam challenges. Okay, let's really dive into this. Why exactly are smart, capable students bleeding marks on these multi-stage energy questions? Well, if you read the actual principal examiner reports, which, let's be honest, nobody does except us nerds, they are incredibly clear on this. The application of the conservation of energy principle to simple and complex examples is consistently, year after year, one of the most misunderstood areas in the entire physics syllabus. Think about a classic multi-stage problem. An object is falling from a height, losing gravitational potential energy, gaining kinetic energy as it accelerates, and simultaneously doing work against air resistance, which dissipates thermal energy to the surroundings. When you are given a problem like that, the examiners aren't just looking for some magical final number at the bottom of the page. They are grading your procedural logic. They are strictly looking for what we call the method mark strategy. When Alex dumps raw, unconnected facts, or when Sam rushes and just writes down a final numerical answer without explicitly showing the transfer of energy from one specific store to another, the examiners literally cannot award those crucial method marks, even if the final number happens to be right. You are essentially hiding your reasoning from the very people who are desperately trying to give you points. It's like pitching a brilliant business idea to the board without showing them the financial model. They're going to reject it. So, here is our strategic roadmap for today. This is how we transform abstract physics equations into actionable, mark-securing steps. First up, the energy conservation challenge. Second, we'll lock down the core physics principles. Third, the procedural framework. Fourth, critical data interpretation. And finally, top examiner warnings. Let's get straight to work. Section 1. Core physics principles, beyond superficial breadth. Let's start with the absolute bedrock, the foundational architecture of your exam answers. Kinetic energy is exactly half the mass times the velocity squared, and the change in gravitational potential energy is mass times gravitational field strength times the change in height. Now, honestly, anyone can memorize these formulas. You probably knew them years ago. But the Cambridge assessment framework doesn't reward rote memorization. It prioritizes deep analytical depth. Cambridge physics candidates must demonstrate total mastery of these fundamental principles by showing clear causal relationships. For instance, you need to understand that because velocity is squared in the kinetic energy formula, doubling the speed doesn't double the energy, it quadruples it. Examiners love testing that specific relationship. When an object falls, the decrease in its potential energy store is exactly equal to the increase in its kinetic energy store, but only if we assume no energy is transferred to the surroundings as heat or sound due to friction. The syllabus demands that top-performing students exhibit connected, conceptual understanding that they can instantly transfer to totally unfamiliar contexts. You need to explicitly state these principles in your answers before plugging in a single number on your calculator. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Trust me, building these foundational habits with us every week is how you guarantee those top grades. And this visualization right here brilliantly illustrates the wider concept of energy transfer. We've got total energy input, useful energy output, and wasted energy output. If we go back to our corporate boardroom analogy, think of this as your company's financials. The total energy input is your gross revenue, the wasted energy output is your operational overhead and losses, and the useful energy output, That's your actual net profit. This is the exact conceptual mathematics behind Sankey diagrams. In a standard Sankey diagram, the proportional width of the arrows represents the exact amount of energy in joules. The total energy flowing in absolutely must equal the total energy flowing out, split perfectly between the useful and wasted energy streams. By visualizing energy this way in your written answers, you are proving to the examiner that you understand the conservation principle at a macro systemic level. It's not just abstract numbers floating in space, it's a physical, quantifiable flow of energy. If you can communicate that flow clearly, you're securing marks that students like Sam completely miss.
Now look closely at this side-by-side comparison. It's night and day. An average answer, like Alex's over here on the left, provides totally isolated facts. It's just a data dump. It lacks any analytical depth. But a top answer? A top answer brings in the PEEL framework. Yes, PEEL. Point, evidence, explanation, link. You probably thought that was just for history or English, right? Actually, scratch that. It is an absolute secret weapon for physics extended response questions. A top answer shows intense analytical depth and cross-topic connections. It makes a clear point about the energy transfer. It provides evidence using the specific data given in the question. It explains the physical principles at play, and it links the whole thing back to the specific command word in the prompt. The principal examiner reports explicitly highlight that candidates who reference cross-topic connections, for example, explicitly linking the kinetic energy of a braking car to the thermal energy generated in the brake pads via friction and specific heat capacity, achieve significantly higher marks. They decode the command words perfectly, and they construct a narrative of physics. They aren't just doing math, they are explaining reality.
Section 2. The procedural framework, securing method marks. Let's act as your strategic exam consultants and totally decode how you should process the paper. Here is your 5-step standardized sequence that you need to run every single time. Step 1. Deconstruct the question. What is the specific command word? Are they asking you to calculate, to describe, or to explain? Because describe means say what happens, but explain means say exactly why it happens. Mixing those up is fatal. Step 2. Extract relevant data. Pull the numbers, the units, and the hidden assumptions right out of that text block. Step 3. Select your analytical framework. Are we using the PEEL method for a long descriptive question, or are we setting up an initial energy equals final energy algebraic equation for a complex calculation? Step 4. Execute with clear notation. This is absolutely critical. This means showing you're working out step by step, line by line. You want to let the examiner actually see the red pen marks transforming into green check marks as they follow your flawless logic. Step 5. Present with correct terminology. Remember Sam, our rusher? Sam lost a ton of marks here by just writing energy goes down instead of gravitational potential energy store decreases. If you rigorously follow these 5 steps, you literally build a physics success blueprint. It makes it virtually impossible for a strict examiner to dock your method marks. Now, to make absolutely sure this procedural framework sticks in your brain during the intense, sweating pressure of an actual exam, you need an actionable memory hack. We have our framework: deconstruct, extract, select, execute, present. DESEP, DSEP. I highly recommend you create your own personal mnemonic for this right now. Something like, does every student expect perfection? Whatever strange phrase works for you and gets locked in your head, I want you to write it at the very top of your rough working paper the exact second the exam begins. It instantly anchors your strategy. And hey, speaking of strategy, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Seriously, do it now. Your future self will thank you. Section 3. Critical data interpretation, proving your analysis. Let's move to the next level and see how this builds your analytical power. We are going to run a quick interactive workshop right now. When you first face a massive, complex wall of data or a terrifying graph on page 7 of the exam, your immediate challenge is the data scan. Imagine a complex data table on screen. I'm putting 60 seconds on the visual timer in your head. Go. You must rapidly extract the core trend from the texts and tables. Next, you have to interpret the specific relationships. Is the kinetic energy increasing at a steady, linear rate, or is it curving upwards exponentially because the velocity is squaring? Then you must draw firm, evidence-based conclusions. But listen up, because here is exactly where the top 1% of Cambridge students completely separate themselves from the pack: identifying limitations and assumptions. When we mathematically equate an object's initial potential energy to its final kinetic energy right before it hits the ground, what massive assumption are we actively making? We are assuming 100% efficient energy transfer, and we are assuming literally zero air resistance. Stating that assumption out loud in your written answer is pure, unadulterated gold to a principal examiner. It shows you actually understand the physics of the real world, not just the textbook world.
Now, let's consider comparative analysis. Quite often, especially in paper 4 or paper 6, you will be explicitly asked to compare two entirely different energy systems or experimental setups. Rigorous comparative analysis requires you to explicitly identify both similarities and differences. You absolutely cannot just list a bunch of facts about system A, put a full stop, and then list a bunch of facts about system B. That's not a comparison. You must use strong comparative connectives like whereas, similarly, or in contrast. Imagine another timer on the screen, 30 seconds. Your goal in an exam setting is to quickly speed write one perfect Peel paragraph using this matrix framework. You point out a clear similarity. You provide hard numerical evidence from the data table. You explain exactly why it happens using underlying physics principles, and then you link it right back to the original question. That is how you aggressively dominate data interpretation and secure maximum marks.
Section 4. Top Examiner Warnings. The Principal Examiner's Report.
We have painstakingly combed through years and years of actual Cambridge Principal Examiner reports. We've read the documents so you don't have to, and we found exactly where thousands of students are needlessly dropping letter grades. It turns out there are exactly 3 critical, highly repeated mistakes that show up year after year regarding the conservation of energy. Let's make absolutely sure you never make them. So, the crucial point is this. Avoid these 3 specific traps at all costs. Number 1, forgetting proper format. This means missing standard SI units, like joules or watts, at the end of your answer, or not showing the algebraic rearrangement of your formula before inserting the actual numbers. If you just write a bunch of numbers multiplying each other, they hate that. Number 2, failing to check presentation. Strict conventions really matter in science. Use proper headings and tables. Draw incredibly clear ruler-straight annotations on your Sankey diagrams. And for goodness sake, make your mathematical working legible. Number 3, and honestly, listen closely because this is the biggest one by far. Answers not specific to the given context. If the exam question asks you about a roller coaster plunging down a 50-meter drop, your written explanation of kinetic and potential energy transfer literally has to mention the roller coaster carts, the metal track, the specific friction between the wheels and the rails, the thermal energy dissipating into the surrounding air. Generic copy-pasted textbook definitions like energy cannot be created or destroyed will score you 0 marks if they aren't explicitly tailored to the specific scenario provided on the paper. Finally, we have a direct, verbatim examiner alert pulled straight from the grading reports. Candidates consistently confuse key terminology. Always define terms before using them in extended responses. Clear scientific communication is totally non-negotiable. Don't just lazily write gravity, you need to write gravitational potential energy. Don't just say the object has movement, you must say it has a kinetic energy store. This strict, unwavering adherence to correct terminology, combined with the Peel framework we discussed and your new careful time management matrix, forms the complete holistic physics answering system. It's a system designed from the ground up to guarantee top marks. We've covered a massive amount of ground today. We've locked down command word decoding, the precise application of the Peel framework for physics, and the crucial time management matrix to stop you from rushing like Sam. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So I leave you with this final provocative question. How will you apply the method mark strategy in your next past paper? Will you continue to panic like Alex and lose easy marks, or will you use the DESEP framework to confidently secure every single point on the board? Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.